All right, so welcome back to Calc 2. So today we are going to talk about the method of shells contrasted with the method of discs and washers that we did yesterday. Okay, so why do you need two? Why do you need to know more than one? Because you think it's already complicated enough. Yeah, it is. So what if we have the function y is equal to 2x squared minus x cubed? Okay. And I'm going to go ahead and draw us a little picture of this thing so we can factor out an x squared. We have a 2 minus x. Notice that we have a cubic, right? And the leading coefficient of the cubic is negative, so it's going to look something like this for our end behavior. We've got intercepts at 0 and 2. So the part that I'm really caring about, because this is between, x greater than or equal to 0, is something that's going to look like this. Okay. Now I don't know exactly where this this turning point is. We could take our first derivative, set it equal to 0, and solve, right? We could do that. So we could figure this out. I guess it would be 4x minus 3x squared, and then solve all of that. But we're not. That's not the point that we're doing today. Okay, so there's our function. And the goal here is we're going to see what happens when we revolve around the y-axis. So we want to revolve here. Okay. So remember that with the method of discs, right, we have to go ahead and divide it up into little pieces like this, right? And we're going to take our right function minus our left function. Now, here's a problem, because we've only got the one function, right? So what we would have to do is we would have to get the inverse function for this, okay? And then we would need the turning point, because if you remember anything about inverse functions, you remember they have to be a one-to-one function, right? And we'd have a little bit of a problem here, wouldn't we? Because it's not one-to-one. It has a turning spot, so we can't do that. So we'd have to have two inverse functions, one on the right side, one on the left side, and figure all of that out. And that is just getting exhausting talking about it. Okay, so fortunately, there's a better way. So what we're going to do is, instead of taking a perpendicular slice, we're going to go ahead and take a parallel slice to this, and we're going to take this little sliver and rotate that around and add up all these tiny little slivers that are here, okay, by rotating all of these around and then adding them up with an integral. Okay, so that's the goal that we're looking at for this one. All right, so that's why you need two of these things, because doing this with cylinders, what we did yesterday, is going to be a major pain. Doing it with what these are called shells. Okay, so we're adding up all these tiny little shells. Adding up all the little shells is going to be far easier. Okay, so again, they typically tell you which one to use, and since I'm copying them out of WebAssign, I'm not really trying to trick you with different questions or anything like that. Normally in a face-to-face class, I would just write this one down and say, estimate the volume, or determine the volume of revolution about the y-axis. And then you can stare at it and try to figure out, like, which one of these do I want to use? And after a while, kind of come to the conclusion that it better be this one. Okay, it better be this method of doing it. But that's not always the way that's going to work. Okay, so let's start with the same thing, okay? Because really, right, we're talking about, this is still a cylinder, right? This is still a cylinder. So what we're going to do here is we're still going to start off with this pi r squared h, okay? And what we would do is we would take this thing here, right? We take this part minus that part. But let's just do it in the abstract for a moment, and then we'll go around to doing it in a little bit more of a thing, a little bit more of a detailed rule. So with our volume of two cylinders, right? outside minus inside. So we're going to have our, well, let's remember this, where this comes from. So let me go back one little thing, right? So our volume is equal to pi r squared, and this, we'll call this the outside or the right-handed one, h minus pi r squared, and this is the inner h. Okay, so outside volume minus inside volume. Okay, so the same thing, doing it this way. Outside volume minus inside volume. So we are still thinking about this as if I was going to take this guy, right? We've got this outside volume minus this inside volume in order to get this value. Okay. So what I'm going to do here is I'm going to factor out, right? We can say this is pi, and then I've got an r out squared minus an r inner squared h. Just took the h's, factored them off to the right, took the pi's, factored these off to the left. Okay, there's no real reason why we do that. Later on, when you get to linear algebra, that's actually a thing of left factoring and right factoring because they don't commute. But for this, we don't really care. Okay, I'm just leaving it this way because there's going to be a d in here somewhere, and that's where the h is going to end up taking its place. So we have pi. Now this, right, if I said, if you were an intermediate algebra at this point, and I said, hey, I'd like you to factor this, you would look at this and say, oh, thank goodness. It's a difference of two squares. This is an easy problem, okay? So what this is going to be, this is going to be a r out plus rn times r out minus rn, right? This outer radius minus inner radius, outer radius plus inner radius, and then we have our h. So, okay. Now we're going to get a little bit fancy. So what I'm going to do here is we are going to multiply by 1. All right, we're multiplying by 1. So what I'm going to do is I'm going to take this 2 here, and then I'm going to push it over here. So this is going to be 2 pi. We're going to have r out plus rn divided by 2. We have r out minus rn times h. All right. So what we're doing here is we're trying to figure out like the values here. Okay. What we're trying to do is figure out the values here. And r out plus rn divided by 2, I'm just going to say like maybe that's our average, right? Min plus max divided by 2, that would be an average. So if we have a 2 pi, we're going to call this r average. Okay, that's the average distance that we're dealing with, the average radius. Okay, now remember that r out minus rn, actually I'm going to change my thing here to looking at this thing. Okay, and we're trying to rotate about this. Okay, this r out minus rn, this is a very small value, right? This is r out minus rn. I should have given you the right picture to start with. Okay, r out minus rn versus the average value, which is going to sit here and be, so this red one, if I can kind of strike a path through the middle here, this is my r average. Okay, so the r out minus rn, that is going to be my delta, right? That's a delta value here. And what is it deltas of, right? Here's my x's, right? Rx is the, r out is the big X, rn is the little x. So this is just going to be our delta x, right? And then how tall is this thing, right? Well, how tall this thing is going to depend on what x is, right? That's going to be your f of x. That's your height. All right. So how far is our average out from my axis? It's x. Okay, that's the value that we have here. No matter which one I pick, the value out here is going to be x. So we're going to have 2 pi x, that's my average. I'm going to change where this is, f of x, this is your height. Okay. times, and we're going to have our dx for this tiny little sliver in here. So this is your circumference, right? So circumference times the height times this tiny little width. And that is going to be our cylinder that we're going to add up. Okay, so we are going to add up all these tiny little cylinders here. Okay, and this volume is going to be the integral from wherever to wherever, okay, of 2 pi x, this is your circumference, times your height, times the thickness. And that's how we're going to be adding all of these pieces up. All right. So it's yet another formula you have to remember, right? The first one was pi r squared h, and the h was the dx because that was perpendicular to this thing. In this case, the dx, or the thickness, right, is parallel to the axis of revolution. Okay, so if you're going to do the washer method, your dx or dy, right, is perpendicular to axis of rotation, right? If we were doing it that way, if we were going to do it right with cylinders, we would have to have little tiny slivers like this rotating around. Okay, this case, here's my axis, here's the little cylinders that we're adding up. These are parallel to, right? So cylinder method, shell method, dx or dy is parallel to axis of rotation. Okay, so I'm trying to give you a couple of different ways to remember, like, how am I setting this up, and which direction am I going in, and how am I going to actually work this thing out? Okay, because there's similar methods, there's similar ways of thinking about it, and I'm just trying to get, like, well, what's the best way to kind of remember this? So in this case, we're taking this little piece here, rotating it around. Otherwise, we would take this little piece here, right? We'd still be rotating it around, but notice we're just picking out different things, different slivers that we're adding up. In this case, it's a sliver that goes in the shell way. This is the way that's the cylinders that we're adding up and going from 0 to the top. Okay. This is kind of nice because if I wanted to go ahead and do this integral, okay, I don't have to worry about trying to factor it or solve for a different thing. I mean, sometimes we still do, but I don't need to worry about like a weird inverse function where I've got a plus or a minus and the plus one is the right hand. No, we're just taking the top minus the bottom. That's it. That's all we're doing. Okay. So if I wanted to get this value, okay, we'd have 2 pi x times f of x times dx. Okay. And again, I completely get it. If you are looking at this, like, I'm going to have to memorize this formula. Like, there are times where you're going to have to. Okay, this might be one of those times. Okay, and we're going to integrate this thing all the way around. So this function, right, the area of interest is going to be from 0 to 2. Notice my dx, right? So this is x equals 0 to x equals 2. If it was a y value, we would take our y, we'd have to figure out where the top of that function was. Okay, so if it was y's, the limits have to be in y's, right? dx limits are in x's, dy's limits are in y values. Okay, so again, we're trying to make sure they match up so that you're sure that you have the right technique and you're sure you're setting things up properly and you've got everything that's kind of, you're making sure that everything is related to each other. Okay, but this one isn't so bad, right? I mean, this integral, right, we can 0 to 2. We have our 2 pi, which we can pull out in front. We have an x, right? What do we have here? We had x cubed minus 2x squared, or what did we have? That was 2x squared minus x cubed. Sorry, let me change that around. All right. So this was x times 2x squared minus x cubed. So again, we still have, right, circumference. So here is my circumference. Right, here is the height. As far as the thickness goes, right, that was our dx. So not, not the best integral in the world to deal with, but because we have to do a little bit of multiplication here. But overall, not too taxing, right? This is not a terrible integral to deal with. This is 2x cubed minus x to the fourth dx, and then we just integrate this thing. It's 2 pi. And what do we have here? We have 2 over 4x to the fourth minus 1/5. Oops, wait a minute. Yes, no, that's right. 1/5 x to the fifth. 0 to 2. Okay. So fortunately, right, we don't have any cosines in here. So if I plug in 0, we're just going to get 0. So that's nice. So we just have to evaluate this at 2. Okay, so it's 2 pi. 1/2. 2 to the fourth is 16 minus 1/5. 2 to the fifth is 32. And that should be okay. 8 minus 32 over 5. That's 40 over 5, right? 8 is 40 over 5. Minus 32 over 5, so that should give me an 8 over 5 value there. So this thing would be, this volume would be 16 pi over 5. Okay. So that's kind of what we're looking at today, is just changing this around and trying to figure out volumes of revolution from a different viewpoint. Okay. So let's see here. We have that. We have that. Here's my little derivation that I finished for you guys. Let me go through. So I messed up, so maybe don't show that part of that. Okay. So here's the problem statement that we have for the next one, just to show you that it doesn't matter which way you do this. Right. What if we had y equals x and y equals x squared? That's the region that we're going to rotate about. Okay, so the region bounded by rotated about, again, the y-axis. Okay, so let's draw this thing. So here's my y equals x, right? And if it's between 0 and 1, right, you square fractions, we get numbers that are smaller, okay? Like 1/2 squared is 1/4, right? So it dips down, okay? And we're trying to rotate it around here, all right? So we have our choices. We could either take a bunch of shells and rotate these around, or, right, we could figure out this thing and add up all of these guys. Okay, and we're going to do it both ways. Okay, this is an easy enough problem, right? We have 0, 1, 0, 1. But in this case, right, we need our dy's here, right? These are dy's that we have to add up. These are dx's that we have to add up. So if I have dy's, we have to change this to, this is now x is equal to the square root of y. This is why I picked y equals x. Okay, so it doesn't really matter this way, which way we're going to do it, right? It's the same. But for this one, we either need y equals x squared. In this case, we have x equals square root of y. Okay. So, and again, right, top here is 1. It's a very nice symmetric problem. Okay, it doesn't matter really which way you've looked at it, you're going to get very similar results. Actually, you should get exactly the same results when we rotate this thing around because it really is the same piece. Okay, so this is just to show you that yes, it does work in either direction. So here's the plus and the minus. A lot of books just say figure out the volume of revolution about this axis, and they don't tell you, well, you should pick this way. They just don't say it. They insist that you do it. They let you choose. In Calc 2, that's infuriating because you know, you're learning them and you don't really know which way to use, and you're going to use the one you feel more comfortable with. Chances are it's this one, and it might be a harder problem to do that way. Actually, your choice is usually going to be this guy right here, because cylinders make more sense than shells. At least they always did to me. But it may not always be the easiest way to go. So what I'm telling you is that later on, they're just going to tell you to find the volume, and they're not going to say, do it this way. It's like, it's up to you. Okay. So let's work it. This is what we did yesterday. Let's do that one first. Okay. So my volumes are, right? My volume is equal to pi, and then we have outer minus inner, and then my thicknesses are dy's. Okay. So the functions that I'm working here, these are functions of y, right? This is an f of y minus a g of y. All right. My integral limits, this is going from y is equal to 0 to y is equal to 1. We have pi. What's my outer function here? Well, in this case, right, this is x is equal to the square root of y. So this is the square root of y squared minus, what's the inner function? The inner function is just x equals y. So minus y squared. And then we have our dy. Okay. So not, you know, again, these are not the most terrible integrals in the world. This is kind of nice. So we have a pi integral from 0 to 1. Again, these are y's. Square root of y squared is going to be y minus y squared dy. Okay. So let's go through and do that. We have y, right? We have right, y squared over 2 minus y cubed over 3. We're going from 0 to 1. When I plug in 0 here, we get zeros. So this is going to be pi. We have a half minus a third, and a half, and I know that that is a sixth. All right, hooray, we got a good answer. All right. Well, what if we try it the other way around, right? We tried this way. Let's try 2. Let's try to add up all the shelves. Okay, so notice that the piece I have here, right, is parallel to, not perpendicular to, but parallel to the axis of rotation. My thicknesses here are dx's. All right. So what we want to do is we want to set this thing up as 2 pi r, right? That's my distance. It's the distance from axis of rotation times height times the thickness. And we're going to add all of these up. And instead of in y space, right, instead of looking at y's, my thickness is going to be dx's. So these are going to be x equals. Okay, so this is x is equal to 0 or x is equal to 1. Okay, so this is equal to, right, 2 pi x, that's my circumference because this is the distance, x is the distance from the axis of rotation. The height, right, the height is going to be y equals x minus, right, y equals x squared. So we have x minus x squared dx. So let's go ahead and evaluate this thing. All right. So let's have a 2 pi out here. We have integral. We have x squared minus x cubed dx. So this is equal to, going from 0 to 1, 2 pi, this is 1/3 x cubed minus 1/4 x to the 4th from 0 to 1. Well, again, fortunately, if I plug in 0 here, right, we're going to get zeros. So if I plug in 1, this is simply going to be 2 pi, and I'm going to have 1/3 minus a 4th. Right? A third minus a 4th. That's going to be 4/12 minus 3/12. It's going to be 1/12. So we have 2 pi times 1/12. The 2's cancel. And of course, we get the same answer. All right? So either way you did this, you got the right one. Which way was better? That's up to you. Okay, depending on how you want to see this, it's completely up to you. Okay, so if you get a problem or it doesn't matter, technically, I don't really care which way you've chosen. But since I know that people tend to be a little bit faster with this method, okay, rather than the other method, I'll usually pick a problem where it would be extremely painful to do it one way versus another way. Okay, and again, you don't always pick the hardest problem that the student has ever seen. Okay, these are difficult. Just with picking, if I just threw out a bunch of functions and said rotate them, they're already going to be tough. I don't need to look for the hardest thing you've ever done with this. Okay, so realize that if you come across something, it's like, wow, that seemed like a really hard problem. Like, yeah, that's not the point. Okay, we're not always looking for the hardest problem. All right, next. So since we're in the shells method, okay, since we're in the shells part, we're just going to say that we're going to do all of these by method of shells rather than method of cylinders, even though some of these can be done the other way around. Okay, so when they see, I used to hate this as a student, and now I love it. Okay, so we have x times y is equal to 2. There's your function. There's your curve. Okay, and y is equal to 0, and y is equal to 2. Y is equal to 4, and we are going to rotate about the x-axis. All right. So since it's talking about a lot about y's, what we're probably going to do here is say that x is equal to 2 over y. That's probably what we're going to be dealing with here. Okay, but we could also turn this around, right? We could say that y is equal to 2 over x. It's okay. So let's draw and figure out what the heck is going on here. Y equals 0, so we're just rotating this around. Here is our function. Right? Because the way I'm looking at this, right, is y is equal to 2 over x. That's how I'm drawing it, because I can't think sideways like this that fast, but I can think pretty well this way. And we are going, right, from y is equal to 2 to y is equal to 4. So what are my x values in this case? Okay. So what are my x values? Well, x is equal to 2 over y, right? So when y is equal to 2, x is equal to 1, right? And when y is equal to 4, x is equal to 2 over 4, which is equal to a half. All right. So if you're looking at this, right, here's a half, here's 1. And we've got this little grouping right here. Now we're going to be rotating around the, oops, are we rotating? Where are we rotating? Yeah, we're rotating around the x-axis. So what we're going to be doing here is we're going to be taking slivers that look like this. right? We're taking slivers that look like this and rotating them around. All right, that's what we're doing with this. So at the end, right, it looks something like that. No holes in it, there's just one piece. Okay, like a tree that you chop down. Okay, this would be like a tree stump type of a shape here. Okay. All right, so let's go ahead and sort this out. So we've got the volume is equal to 2 pi. Right, what are we going for? Y is equal to, because we're going for little y's, right? Dealing with y's, 2 to 4. We have our dy, that's our thickness. Here's our dy. Okay, and we have y, because what's the distance from the axis of rotation for any point here? Right? The distance from that axis of rotation, right, is just going to be the value here. So this is going to be 2 over y, because we're not hollowing this out at all. Okay, so we're not hollowing this out. This goes from the axis all the way up to wherever the y was. Okay, the axis to where y is, and we're just doing that. Okay, so yeah, nice integral, right? So this is going to be just cancel. So we have 2 pi times 2 dy from 2 to 4. So we end up with 4 pi integral from 2 to 4 dy. So this is 4 pi y going from 2 to 4. So this is 4 pi 4 minus 2, which is, I believe, 8 pi. All right. So that's that problem. Okay. And again, you could have easily done this the other way around with the x's. All right, which is why I put them this way. So in case you wanted to check, we could. All right. All right, so let's try, how many more do I want to do here? Maybe 1 or 2 more. Okay. So let's try one that's a little different here. Let's try y is equal to x cubed. We're going to go from y is equal to 8. Okay, x equals 0. All right, and we're going to go rotate about x equals 9. All right, so we have to have some of these just for the sake of dealing with, non-standard axes. You will get one of these again on a quiz or a test. It will definitely put you, one that's not one that's not about the axis. They don't all have to be, but at least one or two have to be around a different value. Okay, let's draw this and figure out what we're doing. Okay, what does y equals x cubed look like? Something like that, right? There's a thing over here, but you guys remember all of your college algebra, you remember all of your shapes. This is why we taught cheap shapes. Here is y is equal to 8. If y is equal to 8, what the heck is x? All right, wouldn't x be 2? I don't know if you're going to need that information, but it's always, I think it's nice to know exactly what we're talking about here. 2, 3, 4, 5, 6, 7, 8, 9. Here's the line. Ugh, that isn't straight. All right, I don't know why I care. I never care about any of the other ones. All right, so here's my thing. Here's the axis of rotation for us. Okay, here's my x is equal to 9. So we're taking this piece here, right, and rotating it around this big axis here. Okay. So we're still doing method of shell. So remember that we're going to be dealing with something that's going to be looking like this. right? And we're swinging this all the way around, all right? And we're taking a whole bunch of these all the way around, okay? So this little piece here, right, that's a dx. All right, that's a dx. So well, we want to set this thing up, right? This is the circumference times the height times the thickness. So the thickness, all right, I've done that part. You guys can do the rest of this, right? Okay, the circumference. Here's our circumference. So we want this whole thing, right? We want this minus this piece here, okay? So let's take a look at that, right? We've got this circumference less this piece, okay? So that's why we're going to be doing a circumference of a minus in here, okay? So circumference is going to be t pi, right? And we have 9 minus x. Any point on here is going to be our 9 minus x here. So that's the circumference. It's 9, take away this part. 9, take away this part. 9, take away this part. All right? Now our height, right? The value that we have to go for our height is going to be this piece minus that piece. Okay, so our height, right? So this is our circumference. All right, and then our height is going to be 8 minus x cubed. Okay, 8 minus x cubed. That's our height. What do we want? This was our height. Okay, and then times the dx. All right. So that's what we have for all of that. Okay, and that is equal to our volume. Okay, and we have to, of course, add these up. We are dealing with the x's. So what are the limits on my x? We're going from 0 to 2. Okay. Now, I understand there's a lot that we're setting up here, and there's a lot that we're trying to keep track of. This is the reason why we draw these things out, is so that you kind of piece all of this stuff together and give yourself a story that you can follow with what's happening here. All right, that's why drawing this out is so important. Okay, and I should probably enlist all of you to be like guest speakers to my pre-calc class, because they're asking, why do we have to memorize what these shapes are? Like, or my calc, actually the algebra class, they wanted to know. I'm like, because if you got to look this up for a calculus problem, you're going to die of old age by the time you finish this thing, because look how long this is. All right. Speaking of how long it is, let's finish this off. All right, 9 minus x, and then 8 minus x cubed, right? dx. Oh joy, now we get to multiply all of this stuff out, right? So multiply this out. So 8 times 9, that's going to give us 72. We're going to have a minus 8x here, right? We're going to have a minus 9x cubed here, right? Positive that, and then a positive x to the 4th. Right? And that should give me my outers, or my firsts, my lasts, my inners, and my outers. Okay, 0 to 2, 2 pi, parentheses, dx. Right? So now it's not so bad of a problem, right? We did all the hard part. The calculus now is nice and easy. Okay, so this is 2 pi, 72x minus 8 times x squared over 2 minus 9, x to the 4th over 4, plus x to the 5 over 5, divided from 0 to 2. All right? Physicists are notorious for this, by the way. Physicists, those guys, they work the geometry of a problem so hard that usually they just end up with that. That's all they want to integrate is dx. It's really nice. So if I plug in 0 to these, we still get all zeros, right? If I plug in 2, right, we get 72. How about 72, not 27? All right. So we get 72 times 2 minus 8 over 2, that's 4, right? And then we have a 2 squared minus 9/4. We have a 2 to the 4th here, plus 2 to the 5th over 5. There's some arithmetic that's going to happen here. Ugh. 2 pi, what is 72 times 2? What is that, 144? 2 squared is 4, so minus 16. 4 times 4 is 16. Let's see, this is 30, this is 16. 16 divided by 4. Right, so this is 16. 16 over 4 is 4, so 9 times 4 is 36. And then plus 32 fifths. Okay. And at that point, I'm like, okay, I'm going to have to punt here because I'm not going to worry about doing all of that. Okay, so 144 minus 16 minus 32 plus 32 over 5. Okay, and we'll go to math, fraction, 512 over 5. Sounds great. 24 pi over 5. Hey, that's a delightful number, isn't it? So that's, following through. Again, I understand. Here's the hard part of the problem, is this. Okay? Here's the hard part of the problem. The rest of this are skills that you've practiced and you were good at and you could do. Okay. We have time for one more? You know what? I'll tell you, we don't have time for one more. We'll pick this up. We'll review tomorrow, and we'll start with we'll do a cylinder, we'll do a shell, and then we'll start with some word problems with some doing some work problems. And we'll probably not finish with this tomorrow. We'll probably do more work problems tomorrow, but I'll let you digest this, and we'll do another problem, one of each of these tomorrow, and then we'll go on and push a little bit further. Okay, so if you end up trying to do some homework, come up with some questions, let me know, and we can do some of those. But I'll give you the rest of the afternoon off here. Okay, so I'm going to go ahead and stop recording.